All right, so last time we were scoping out day 12, the hill climbing algorithm, in which we need to work out how to, given a bunch of heights that are represented in letters, somewhat annoyingly, and a starting and an ending point, S and E, we need to work out what the quickest path is from S to E, in which we can only go up by at most one level of altitude. And do this, we're going to have to use a shortest path algorithm. And so the name of the game today is going to be, can I remember how to implement Dijkstra's algorithm? I never know how to pronounce it or spell it for that matter. So we will try to do that. And last time we had kind of set up the tests to start with. So we're going to have a grid struct that knows how to represent itself as a grid. And then it will be able to get its shortest path. And I went ahead and entered in the shortest path from the example question in here, so we should be able to test that. Cool. So maybe before I jump into, or I continue through, well, actually, let's continue here for a little bit before we get into the actual shortest path part. So we need a new height function, and I'm just going to make a function that sits outside of all the structs. Sorry, not new height, to height. Some character, and it returns some usize. And we can just say C as usize minus A as usize. Character A as usize. And I think that should just work. I suppose we could yell if we don't give it an alphanumeric. Probably not. Or I guess we can say before we return, let's say let to return be this, and then we can assert that to return is less than 25, less than or equal to 25. Return to return. And that way that effectively checks that our input is the right type of thing. Okay. And what else do we have here? Right, we need to implement grid from strings and get shortest path, which we'll just stub out for the moment. So, struct grid, and what does grid need to contain? A vector of vectors should be good. A vector of vectors of usize. It could be U32s also. Don't really think there's a reason to use one and not the other. Seems like we should probably name it. And then equal grid. Oh, and let's drive some stuff. We don't want default. We don't want copy. I guess we want clone. These seem fine. Okay, and then we want pub function new grid vec usize. grid. And then we're going to want pub function get at some position the u size, and that will just be self.grid v.x v.y. We could make that return maybe. Right now it'll panic. I think I'm okay with it panicking. I think I've gotten to the point where I'm deciding that panics are fine in advent of code problems. And then what else we need? Pub function from strings. Strings, code string, self, and we'll just make that unimplemented for the moment. And we'll need pub function get shortest path self, and that will return a vec of vec2s. Find out whether are x and y not functions here? X and y are functions here. So what's the issue? These return I32s. Okay, sure. That's like a little annoying, isn't it? So I mean, one thing we could do is generalize vec2 to take an arbitrary number. Not, like, fantastic. Let's just parse it. Let's see here, how does it work? Is it into, parse into? Something like this. Parse into u size. And then unwrap it. Oh, I can just... There's some parse function. We can't just say into here. Because still won't work, right? Yeah. As to int unchecked is not really what I want. Oh, maybe I can't. Okay. As I32 as usize. Okay, so this works, but only because it does a saturated cast apparently. So we should assert that v.x is greater than 0. Okay. That should be pretty safe for my purposes at least. Okay, and now we have a lot of red down here. So get shortest path. Oh, needs 2 points. Start. End. And it should return an option because there might not be a shortest path. And what? It's a vector of vec2s. Expected a result. Oh, I think an option is sufficient. I think an option is sufficient. So let's okay, some cool. Okay, and then get starting point and get ending point. Okay, which should be members on this guy. Starting point, back to ending, back to, and then this needs to take starting point, ending point. And now we can say pub function get starting point, starting point, and pub function get ending point. Cool. And it looks like we're compiling. Failures because I haven't really implemented anything yet, but okay, cool. Things compile. That's great. What's already passing? Oh, right. There's already the 2 height is already passing. Nice. Making progress already. Okay, so parser first. So how to parse this shouldn't be too bad. We want rows. Grid should be a vector of the rows, and so each string is going to be a row. So we say strings into iter. And what to say here? Parse row s, and that'll already be a set of vectors, and then this will be a set of rows, and we'll just collect it. And oh, we also need the starting point and the ending point. So let starting point, ending point be parse starting and ending points s, not s, strings. And then this needs to be and then we'll just say that rows is this, and we will return self new starting point, ending point, rows, or grid. It should really be called grid. Let me return this. Okay. So now we need a couple of private functions. Parse starting and ending points. We'll take a vector of strings, and we'll return two vec2s. And to do this, it will go through each. I'm not sure there's a faster way, given that these are coming in as strings. Should be called strings. Strings into iter. We're gonna have borrow checker things with the strings in a moment, but that's okay. Actually, do I need to? Yeah. Into iter map, or even, yeah, let's say map s dot find s, and s dot find e. We need to enumerate this. Oops, what happened there? IS. Okay. And we'll make this I comma that guy and I comma this guy. Actually, even better. let's do s dot find. And what does find? Find gives an option, right? Yeah, so dot map. IJ. And same here. Map IJ. Okay. So now we're gonna have, and let's make this a little bit clearer. Okay, so now we're going to have either nuns or we're going to have a tuple. It's going to be a tuple of options of tuples. So they can be either nuns or sums of S and E, or of the location of S and E, I should say. And then we're going to want to collapse those. So something like fold, or what's the other one? There's fold and there's the other thing. Am I happy with fold? Reduce. Reduce is the other one. Reduce should be fine. So we will reduce. And reduce just takes a function of an accumulator and an element. Accumulator and element. And this will be it's an option, it's a pair of options. So let's just stick it in its own function. We'll say match element so if it's sum x sum y, then sum x sum y, if it's sum x anything else, then sum x accumulator 1. If it's anything sum y, then accumulator 0 sum y, and anything else we return the accumulator. Okay, so that's going to essentially stomp. Anytime a sum shows up, it's going to stomp on whatever came before it. We should never. We could put some tests in here that like confirm that we only ever hit one. But but I think it's okay. I think it's relatively straightforward. And then all of the angry compiler messages are because I need to handle the result in the end. So at the end of all of this, we will see here, that reduces, so we'll map, actually wait, what does that reduce to? That reduces that, so that at the end of it is going to return a tuple. So let maybe points be this, and then assert maybe points dot 0 is sum, assert maybe points dot 1 is sum, and then I guess we can just return maybe points dot unwrap, maybe points 0 unwrap, and maybe points 1 unwrap. Okay. Oh, this is an option itself. Okay. We can say expect there should always be at least one element in the strings. And let's be a little bit good here and say points, we'll just say maybe points dot 0 was still none, and maybe points dot 1 was still okay, and then the only issue with this is that we actually need these to be vex. So really, this should be let's starting point be this, and we'll say let ending point be this, and we'll return vec2 new starting point dot 0 as I32, starting point dot 1 as I32, and same thing here. Vec2 new ending point dot 0 as I31, ending point dot 1 as I31. Okay, so that should parse the starting and ending points. Parse row isn't going to be happy with me because, oh, it's not even, well, it doesn't exist yet. The bar tracker is going to be upset with me in a moment, but we'll get to that when we get to it. So parse row s string vec of vec2s, no, vec of view size. And here we'll just say s.chars dot map c to height c dot collect. Should do the trick. Okay. And now the bar tracker's upset with me. Yeah, because I already moved this. Okay. I'm just gonna clone it. Should be fine, I guess. Actually, we can do this, right? We can borrow it. We can borrow it here, and we can say iter that works. That's nicer. Saves us a clone. Sick. Okay. Cool. So now we expect the test to all still fail, except for the one that was already passing, because we haven't actually implemented shortest path yet. I do have a parser test though, don't I? What did I do in my parser test? Parses input. Oh, this should work. So why isn't this working? Attempt to subtract with overflow. Really? Right. Okay, because I didn't handle the starting and the ending points. So we need parse character to return a usize, and this will say match C. If it's S, then 0. If it's E, then to height of E. No, of Z is what the puzzle says. And then otherwise, it's to height of C. And now parse's input is still failing. Oops. Why are we still failing? Still with overflow. Let's put a marker here. T. Still overflow. So the input. What's my input? Input's 12. Bunch of characters. Somewhere in here there's an E, which we should be handling. Somewhere in here there's a capital S. Okay. To height is working. Oh. Is this a line return thing? Still fails. And we know that this is passing for... Oh, did I just forget to... Yeah, I just forgot to say self-parse char. Still though. Okay. New failure. So 2, 5. So the starting point, the ending point are working. 0, 0 is working. 2, 5 is not working. Where's the example input? So 2, 5 should be 0, 1, 2. 0, 1, 2, 3, 4, 5. And should be Z, which we know is 25. Why did I put B here? Should be Z. Presses input still fails. Okay, 2, 1 is 2, 1 is C. 2, 1 is C. That should be 2. What did I say? Didn't say the right thing. Let's just double check these since apparently I didn't do a very good job the first time. 1, 2 should be B. That's wait. No, 1, 2 is also C. 4, 7 is the bottom corner, and that's I. Okay. So that guy's passing. So now we get to do the fun part, which is the shortest path algorithm. Parsing for day 12. Okay. So Dijkstra's algorithm, or Dijkstra's algorithm, or anybody wants to tell me how to pronounce that, I will not be upset. Leave a note in the comments. I guess I could just Google it. Okay, so the idea, and let me pop open a thing. Okay, so the idea is going to be, we have some grid. We want to find the shortest path. And it's been a long time since I've done this. So the key idea in most algorithms, I don't think is an overstatement, is to figure out where you can cheat and skip computations that it seems like you need to do. Either because they're going to be redundant at some point, like most like linear or like dynamic programming problems, like skip redundant calculations, or because you're never going to have to do them. You can ignore them completely. You can prove that they're not relevant. And Dijkstra's algorithm. Dijkstra's algorithm is an example of the latter, where the point is going to be that if we've gotten to, we're going to start at S, the starting point, and we know that, and calculate distances, like distances so far from S to various points. We know that the distance from S to S, I can say S to S, is 0, so we never have to check that again. And then we can update all of the neighbors of S with their distances so far, i.e. 1, all of the valid neighbors. So sometimes it'll be 1, sometimes it'll be infinity, because we can't go there. And then for each neighbor, we can update their neighbors. Starting from the lowest tentative distance. And the key insight is that once we've like visited a node and looked at all of its neighbors, we never need to look at it again. And that's where we're gonna save a lot of work, because and I'm recalling this from the depths of my memory, so sorry to think out loud. Because once you've calculated distances, once you've calculated some distance, some distance, or like the shortest known distance from each of the neighbors of a certain point, you're never going to do any better than that. There's never going to be some sneaky path that can do better, because you're stepping through all the nodes in a way that essentially radiates outward. Trying to think of a clearer way to say it than that. Yeah, so it's like, because we're always looking at all of the, because at first we look at the starting point itself, and then we look at all the starting points neighbors, and then we look at all the starting points neighbors, we will have exhausted all of the shortest distance paths already for the like next ring out. And so we don't have to recalculate a lot of the potential paths, because we've exhausted them first. Maybe that's a way to put it. So something like, so it's going to be like, we know that SS equals 0. So set, we'll call it D of S equals 0. And D of, so far we'll say, we'll call this D of X. D of all of the other vertices equal to infinity. Track the open nodes in a set or a list. We'll call it O. For all open nodes, let's see here, for the next open node, for the minimum, for the open node with minimal D of V, which is just going to be random the first time, but later it will be known. Update all of its neighbors n with a new DFV. Basically, if d of v plus 1 is less than d of n, then d of n, then update it. Else don't. And then if we, when we get to E, we'll know that the resulting d of E is the shortest path. So it's like you can never, you know that you've already got the minimum path, like at any given time, all of the open nodes in your set, like that's the shortest possible distance, the minimal d of v that's still in your open set is the shortest possible distance to anything in your open set. And since your open set still contains the thing you care about because you haven't terminated the algorithm yet, you know that it's going to be longer than that, and you're sort of eliminating, you're pushing outward and keeping that minimal d of v shorter than your set until the moment that you find it, and that means you know it's the shortest path. Maybe that's a nice way to put it. Hopefully that makes sense. Okay, I'm pretty sure I'm getting this right, but we will find out. So how to actually implement this. So what do we need to be able to do? We're going to need to be able to, we're going to keep a set around, I think this can just be a function with some nested functions. I don't think I need extra structs for this. So we'll keep the open set around. We need to initialize the open set. So maybe we can have like a hash set and a hash map. The hash set is the open set. The hash map is the mapping to the distances. And then we need to be able to get to our neighbors. So we should probably implement a get neighbors function on grid, because that's going to be relevant. Here, actually, let's go here. Test get neighbors. This needs to be an actual test. Take this, and we can say assert equal grid dot get neighbors grid dot get starting point, and it should be what? It should be, there's only one neighbor? No, there are two neighbors of the starting point. It should be a hash set, well, we'll say vec2 new 0 1 and vec2 say into iter.collect, and that'll be a hash set. The ending point has one neighbor. Oh no, everything is the ending point's neighbor. They're all equal to or above. Actually, hang on a second. Starting point has 3 neighbors. Because 1, 1 is also a neighbor, which confuses me. Oh, no, it's not, because we can't go diagonally. Okay. But while I'm doing this, let's just split this out. We'll just do it this way. This in the wrong place. Okay. So let's do it with the ending point also. Let's just copy this. And here we will say get ending point. This will be what the ending point is at 2, 5. So it's 2, 4, 2, 6, 1, 5, and 3, 5. If I'm doing that right. Okay. That doesn't test, and then I want to test. Let's just do a case like let's see here. So not the ending point. Let's do a case with where we're at the edge of the board and where there's a jump. So like at 0, 2, there's a jump. And so here the neighbors are going to be, so we can go to the left, we can go to 0, 1, we can go down, which is what, 1, 2, and but we can't go to the right because it would be going really high. Okay, this should be a pretty good set of tests. And let's say pub function get neighbors self chords returns a vector of vec2s, and what to say here. Basically we want to say self.get potential neighbors or get adjacent. I'm really not spelling well today. Adjacent coordinates, and then we'll into iter that, and we will filter on on self dot, let's see here, let current height or coordinates height is self dot get coordinates, and then we filter on self dot get v as I32 minus minus coordinates height as I32 is at most 1, so it's less than or equal to 1, and we collect the result. Yeah, and then put function get adjacent, same function signature. Why is this yelling? Vec of vec2. Oh, it's a vec of vec2. Okay, and then this will just be let's say vec self dot maybe get coordinates plus vec2i and we'll do minus, we'll do plus, we'll do minus, and we'll do j and j, and maybe get, oh, and then we need to filter dot into iter dot filter. Is filter map a thing? Filter map. Yeah. And so this will just be the identity. And I guess this should actually be a hash set. And this can also be a hash set because I don't care about order. There might be optimizations in all of this. I don't care to start out. The only thing I care to optimize to start out is shortest path, because the shortest path is really slow if you don't do it in a smart way. Okay. I guess I have to go implement INJ. Function I self should be self new 1 0. Function J self should be self new 0 1. These are classic conventions from vector algebra if you're not familiar. Okay. So we will import hash set. We will dereference it, that's fine. And we will implement maybe get, which will just be the same thing, but it will return an option. And here we will say what if self dot, if not self dot is out, is in bounds v, then return none, and otherwise we will say self dot get v. And why are we unhappy about this? Duplicate definite. Oh, sorry, that should say maybe get. Okay. And is in bounds. Cool. So this will be cool if I could spell. This will be let's see here. B dot 0 is greater than or equal to 0, and B dot 1 is greater than or equal to 0, and B dot 0 is less than maybe we say let dimensions be self dot get dimensions, and then we say dimensions dot 0, and b dot 1 is less than dimensions dot 1. And last but not least, pub function get dimensions returns 2 u sizes. Those u sizes are, it occurs to me that we should probably be checking something in here. We need to assert that grid dot iter dot all x dot length equals L, and we will say assert that grid dot length greater than 0, and we will assert that grid 0 dot length is greater than 0, and we will let L equal grid dot length. And that way it makes sure that we're not constructing anything other than a square. Oh, actually, does it have to be a square? Maybe it doesn't have to be a square. Doesn't have to be a square, actually. So we'll just get the column length, or the row length. The row length. Okay, but that makes sure that all of our rows are the same length. And we're back on track. Self.get v needs to be wrapped in some. And this is v dot x, and this is v dot y. Dimensions. Those should be fine. What's the concern here? Oh, as u size. As I32. Okay. And dimensions is going to be self dot grid dot length and self dot grid 0 dot length. Okay. And one more failure. We don't know how to collect this into a hash set, apparently. hash set can't, a vector 2 can't be built over. Yes. Accurate. I guess we just want self dot is in bounds x. And this doesn't need to be filter. This should be filter map is okay. Maybe get filter map. Not quite. Oops. I don't need to maybe get these at all. Now that I'm thinking about it. Those are the vectors. And they just are the vectors, and then I just want to filter on whether they're in bounds. And why are these? Okay, sure, I can dereference that, that's fine. Okay. Cool. Everything's compiling. Let's see if our get neighbors function works. It seems to. All right. So we know how to get neighbors now. Do we have all the tools we need to implement Dijkstra's algorithm, which I think is how you say it? I think we do. Let's start. Let's try and see where we get to. Hey CTX, thanks for the follow. How's it going? Get shortest. Okay. So we will need the open nodes unvisited. What's the right word for this? Open is a little bit. Not really open. It's unexplored, unvisited, still to be checked. Yeah, to check doesn't seem terrible. This will be a hash sets of indexes, so a vec2s. And it can be hash set new. And then distances so far is a hash map of vec2 to a distance, could be a usize. And then distances so far we should actually instantiate as self.grid. Let's see here, what's the nice way to do this? I guess it's 0 through, I guess we can get the dimensions first. So let dimensions be self.getDimensions, and then 0 through dimensions 0. Computer zip that with 0 through dimensions 1 to get us a tuple of our dimensions, and then we will map that as ij, and the mapping will be if ij equals, is it vec2 new ij equals self.get starting point, then 0. Otherwise, it's like might be a terrible way to do this now that I'm thinking about it. I assume just populating. Well, you gotta fill the keys somehow. I guess it's okay. I'm not gonna worry about it too much until I find out that if things are really slow. So then this will be a usize max otherwise, because we want to say that's should be as I32 and as I32, because we want to say that the distances are either 0 or infinity, which is essentially going to be usize max in our case. What don't we like about this? Hash map from iterator. Yep, that's fair. I want to say that this is a tuple of, okay, so let's, hang on, let's take this and say let node be this, and say if node is equal to that, then node comma 0, otherwise node comma usize max. And now we're happy. And now we're going to start going through the neighbors. So it'll be while distances so far. Let's see here. It's just for the sake of stuff, we'll say loop. And okay, so one issue here is that going through the hash map by distance is not fast. We need to know what the minimum distance unvisited node is. which probably needs like a priority queue or something. Binary tree. Because we don't actually want to... We're not really looking up the distances that often. We're mostly looking up the neighbors, which is easy. I guess we are looking up the distances, but then the slow thing is going to be starting with the smallest number of, or starting with the unvisited node with the lowest distance. So the structure of the algorithm is basically going to be let minimal let's say let node be to check dot get minimal distance, which isn't a thing, but we'll handle that in a minute. Get node with minimal distance. This is just pseudocode while I think through this. Let neighbors be self.getNeighbors node. So we can even say, so like for neighbor in neighbors. We'll say let new distance be distances so far, node +1, and then for neighbor and neighbors, if new distance is less than distances so far neighbor, then distances so far. I think I have to say dot get here. Dot get. Dot get. No, distances so far. Dot inserts neighbor. New distance. Okay, so we go through all the neighbors, and then we say to check dot remove node, basically. And up here we can say, or maybe it's here. It's here. We can say, we might be able to do it sooner, but this should be fine. We can say if node is, no, we should be able to do it up here. If node is self.ending point, then we need to return, but that also means we need to have been keeping the path around, which we're not doing. So return path to node. Again, this is pseudocode while I sort of sketch this out. To check remove node. Okay. So the problem doesn't actually ask for the path. The problem asks for the shortest path, but I feel like I'm asking for trouble in the second problem if I don't keep the path around, which means that we're actually creating a graph here. So when we get to the node with minimal distance, it should have associated with it a single path. So there's a So if we think about this as constructing a tree instead of as just keeping a single number around, I guess what we could do is keep around we could keep the parent around. We could keep the shortest distance parent around, and then we just walk the tree backwards. I kind of like that. Okay, so the idea would be that distances so far we would keep, but we would also have let parent map be a hash map from vec2 to vec2, and that would just have be a vec2 to an option of vec2. And that would just be self.get starting point none to start with. Right, and so then distances so far is basically is keeping the lengths around, which it's not even clear that we need to do. We're gonna have to walk the tree over and over otherwise, so I think this is alright. And so I'm starting to want to put this into its own struct. Because it's going to be a little bit painful to keep track of all of this. But let's for now just say self get path from parent map, and node. And to get the path from the parent map, we will say from parent map is parent map is a hash map from vec2 to vec2, and the node is just a vec2. And we want to return a vector of vec2, and we want to say need to return be an empty vector. Let mute current be node, while let sum current equal parent map dot get. It's going to be a sum of a sum. Let's just say loop. And here we'll say, we are still going to need the current here. Node. Yeah, we will. And then this is just, at the end of this, it'll be current equals parent map. Of current, I need to get. And we can expect this. The parent map should be complete. And then we'll say to return dot push current, and this still has to be match parent map expect because this can be none, in which case we return to return, and otherwise otherwise C, but I didn't quite do this in the right order, I don't think. Does this work? I don't think this works. No, that's not going to work. That's going to put to return in there. So we want to match first and then set current. So parent map get returns. Oh, this hash map is an option. Okay. And then current equals C, which we can dereference. Might need to clone. No, we can dereference that. Okay. and that's going to push it on, but that's going to be in the wrong order, so we need to reverse this. So that will be the complete path. That will certainly end with the final node. That will certainly, yeah, that will include both endpoints. Cool. So when we insert distances so far, we also might need to change. We also need to say parent map dot insert neighbor node. And this needs to be unwrap or use it. Well, really, this should always be populated. So expect we've already populated the distances so far. So this should be dereference that. Okay, we insert the neighbor. We insert some node. When we instantiated it, we already put in good. And then to remove from a hash set, removes the value from the set. So that should be good. Get path from parent map returns a vec of vec2s. Sure, this should be a sum. Oops. This should be a sum of this guy. What's happening? Keyboard problems. Okay. And at the very end of this, so to check get node with minimal distance could actually return false. So we want to match on this. Some n, then n, none, then we return. Not sure if I can do this. Can I do this? I guess I can. It's ambiguous whether this return to me it seems ambiguous whether this return is return. I guess I would need a block to be open for it to return to node rather than returning from the function that it's in. I guess that's how that works. And now we just need a way to get the node with the minimal distance. And I mean, the easiest way... Actually, you know what? Let's actually say if ttrack.length is 0, return none. And for now, this will be tcheck iter what is try find? Will try find work for me? Applies a function, returns the first true. Oh, nice. Yeah, that will work. And it will be. Oh, but I want the minimal. Try reduce. It's gonna be really slow. So maybe rather than having tcheck be a hash set, you can have it be a sorted list. And then we can we want to insert, we want to remove and insert efficiently though. That would be a binary tree, same problem, it's going to shuffle around all over the place. Alright, let's just do it this way for the moment, and then we'll optimize when we need to. So and it's going to be calculate a sum of a series of numbers. So if distance is so far, I is less than distances so far, A, then I else A will work, I think. What is try type about? Oh, it's distances so far dot get. Dot get. I'm not convinced this does what I think it does, though. How about just reduce? There we go. Okay, so that gets me an option, which we already know something's going to return. So we can just expect we already checked for empty. And now, and we can pop that out. Okay. So, distances so far, dot get. And this returns an option. Again, we can say expect we've fully populated distances so far. Okay. And we should declare these mutable. Sure. Check mutable. Okay, and things compile. So there are definitely some slow bits in here. It seems like we're redundantly keeping track of distances so far, and the parent map and this thing where we find the minimum by like going through the set and reducing is definitely slow. But let's start with this and iterate from there. Okay, so get shortest path is not quite working out for us. So it's giving us none back, even though there is one. Okay, so in the trivial case, we're getting none back, which is not what one would expect. So start and end are the same thing. Distances so far get set up. Parent map just has the one element in it. ToCheck should have one element in it. Oh, it doesn't at all. Everything should be in ToCheck, not nothing. Not nothing. So actually, let's take all of you. And say dot map ij vec2 new ij collect. Whoops, we need this to be up here. Okay, and then this can be ToCheck dot iter should do it, I think. And then this will just be this will be V, and this will be we just call this node. Okay. And then we have to dereference here. And does. Whoops. Compiler doesn't like me. Oh, because I don't need to make this. No, I do. Because these need to be as I32 and as I32. Okay. All right. So we've already populated distances so far. Is what we're saying. So distances so far, we took everything into check. Which should be all of the dimensions as vectors. And we populated the hash map. Get neighbors. But this has no neighbor, or has no entry, and it is neighbor. I have to format these. Okay. 1, 0 has no entry. That doesn't seem right. So to check, certainly 1, 0 would be in there. No, it wouldn't. That's not how this works. Okay, self.get what, all? Get coordinates, let's say, and this is going to be a function get coordinates self vector of vector 2, and this will be let dimensions be self.get dimensions 0 through dimensions 0. Zip that with 0 through dimensions 1. No, that's still not right. We have to map that. Map it. Those are I. And then 0 dot dimensions 1. We map to J, and we say IJ, say vec2 new, I as I32, j as I32, and then at the very end of this, we flatten. And this almost worked. Do we have to collect at the end? I didn't remember that we had to collect at the end. Maybe we have to collect here. We do have to collect at the end. Okay. Clean this up a little bit. Okay, so that should give us the right number of things. We missed a get coordinates. We will say into error. Okay. And then we will need to, we don't need to map this at all. We just collect it. And we don't need distances at all. And what's wrong with this? Into iter, j is a u size, ij. What's the problem? Force closure, use the move keyword. I can't do that. It's not going to want to move multiple times. I say dot clone. No. Can I say? If I say this, yeah, it's not going to like that. I don't want to zip it. And zip it with repeated I. I assume it's not suggesting this, is it? No. I guess I can always say I comma j here, and then iter repeat I dot zip like this, because now repeat I is just I over and over again, and then we zip it with something of finite length, and when it gets zipped, that should be the right size. I believe that should work. Okay, we got an answer. It was not what we expected. Hilariously, I think it may have solved the problem, the full problem, because it stops at 2,5, which is hilarious. So my bug is actually solving the problem, but that is not really what we want. But it means we're getting very close. So let's just step through this. Figure out where it's going wrong. in a few minutes, so hopefully we can get through this. So 2check should be big. Node should be 0, 0. Variable is optimized away. Okay, node is 0, 0. If node equals ending point, we return, but that's not what we wanted. We want to return if node equals the end. Okay, so we cleverly did not use our own function very well. This should be end. This should be start. And this should be start. Okay. And what about now? Let's go back to our test. Okay. Okay, cool. So the only issue here is order, which is fine. We don't actually care about order. Oh wait, no, we do care about order. Okay, but these might be, this is actually ambiguous, I think. So if I look at the question, if I want to go from 0 to 1, 1, yeah, I can go in either direction. So that's ambiguous, and I'm fine doing it this way. All right, and then this one is disagreeing with me here very slightly. I'm sure I just copied it wrong. Like it goes to 2.5. It probably has the right length. Let's just check that it has the right length, and I'm fine if I just copied it wrong. So what's the easiest way to do this? To space, we will turn into a new line. And now we will just look at all of this, which is 32 long, but that's to be expected because we're counting both the starting and the ending points. Okay, so what's the easiest way to, let's see, let's just copy all of this and go to our problem and paste it in here. And we will just get rid of all of these, and we will fix this. 2 new. Something like this. Okay. And I mean, broadly, does this look right? It goes down, it goes over, it goes down all the way to the bottom, it goes over. Wait, 0? Yeah, it goes up, it spirals around. Yeah, this broadly looks right. Failed. Oh, this is probably not always going to be defined. I'm just going to say that length here is 3. Because I don't want to deal with the ambiguity. Get shortest path. Actually, length should be 4. Now that I think about it. Get shortest path returns a... Okay, we can unwrap it. Fails. I guess it is... Oh, it's 3. Of course it's 3. There's going to be an off by 1 error at the end of this. But... And... Oh, what's going on here? Is it ambiguous? It might just be ambiguous. There might be 2 paths. And that's why it's not the same. If I run this multiple times, does it sometimes pass? No. Yes, it sometimes passes. Okay. So there are multiple paths. It's... which is fine. So let's just say that dot unwrap dot length is 32. And now this should pass. Okay. And I really do need to go. But I want to see if we get an answer. Sure. So this is going to be from input shortest path be grid dot get. Just give me 1 second. Okay, let's finish this up in the next 5 minutes. Get shortest path, grid.get starting point, grid.get ending point, and then return shortest path dot length dot unwrap dot length -1 because it includes the starting and the ending points. Okay. And it thinks. Might be a little bit slow. That wasn't too bad, but I have a feeling part 2 is gonna test us on this. We'll have to optimize, but 517 is the answer that we are given by the coding gods. Let us throw that in there and let us see how we do. 517. It's the right answer. All right. So that is problem, whatever that is, problem 12A, done. Next time, I imagine, we'll be doing a slightly harder optimization problem with part B, but I'm going to save that for tomorrow. For now, I will just commit solve problem 12A. And let's see if there's anyone around who we can raid. Nope, nobody online right now, so I will call it there. Thanks for watching. Kind of happy that I was able to get Dijkstra's algorithm implemented without too much trouble, without having to look it up. And I'll see you all tomorrow at 1 p.m. Eastern. Take care.